In this video, we'll learn about self-organizing maps, SOMs. This video was produced in Korean and then translated into English. The audio was generated by AI, text-to-speech. In the previous video, we looked at a competitive learning model. In this video, we'll explore a self-organizing map model using the competitive learning. Let's take a quick look at the self-organizing map. We will then look at how to find the winner neuron and its neighbors, and update the weights connected to them. Finally, let's implement the SOM models to cluster the Iris and MNIST datasets. The self-organizing map, SOM, was introduced by the Finnish professor Teuvo Kohonen in the 1980s, and therefore is sometimes called a Kohonen map or Kohonen network. The structure of a simple SOM network is as follows. It consists of an input layer and a two-dimensional competitive layer, and the neurons in both layers are fully connected. This is an unsupervised neural network that uses competitive learning, which we explored in detail in the previous video, to reduce high-dimensional data into lower-dimensional, often two-dimensional, maps. For example, a 784-dimensional MNIST image vector is reduced to a two-dimensional vector in this space. The SOM operates in two modes, training and prediction, or mapping. During training, the SOM chooses a winner neuron in the competitive layer for a given input data point. This is identical to the competitive learning model. And then it selects the neighbors close to the winner neuron. For example, in this figure, this is the winner neuron for a given input vector. These are the neighbors close to the winner neuron. And these are the neighbors a little further from the winner. At the beginning of the iteration, set the neighborhood size large. We elect a winner neuron for a given data point and select neighboring neurons around it. Then, we update the weights connected to the winner and neighboring neurons according to this competitive learning rule. In the next iteration, we reduce the neighborhood size a bit. Then we elect a new winner neuron and select new neighboring neurons around it. As the iterations progress, the winner may change. After many iterations, the neighborhood size will be reduced to 0, leaving only one winner with no neighbors. This will be the real winner. The strength of the weights for the winner and the neighbors can be adjusted using the following functions. A Mexican hat, a stovepipe hat, or a chef's hat-shaped function. The winner neuron is at the origin. The x-axis represents the distance from the winner neuron, and the y-axis represents the strength of the connection weights. When using the Mexican hat function, the winner is given the greatest weight, and the neighbors are given smaller weights. For example, the weights connected to the winner neuron are updated using this formula, and the weights connected to the neighbor neuron located here are updated using this formula. When the distance away from the winner is larger than the certain distance, the value of adjust weight is a negative. For example, the weights could be updated like this. Then, these neurons are inhibited from being activated. Then, if go on farther, the strength increases slightly again, becoming positive. It is said that the human brain learns in this way. This is a bit complicated to implement, so we can use a simpler function called stovepipe hat instead. Alternatively, we can use a much simpler function called chef's hat. This function updates the winner neuron and its neighboring neurons with the same strength. In this video, we will use this function to implement SOM models. In the prediction phase, each input data point is mapped to the generated map. For example, if this is the winner neuron for the MNIST digit 0, that digit would be mapped here. MNIST images that resemble the digit 0 tend to map to this region. And for example, MNIST images that resemble the digit 8 would map to this region. Then, similar images are clustered on this map. The SOM can be used for clustering, dimensionality reduction, anomaly detection, data visualization, etc. Next, let's look at how to find the neighbors of the winner neuron. Let's say we have a 2D competitive layer with 10 by 10 neurons, like this. The small circles represent neurons, and the numbers inside them represent the neuron indices. If the maximum distance between the winner and its neighboring neurons is 2, and the neuron 11 is the winner, then these neurons marked in green are the neighbors of this winner. Since there are no neurons with a distance of 2 on the top and left, only these neurons with a distance of 1 are neighbors. The code to find neighbors can be written as follows. When k is 2, the neighbors of neuron 11 are as follows. You can get the same results as shown in the figure on the left. If we represent this as a 1D competitive layer with 100 neurons, the neighbors would be as follows. That is, in one-dimensional space, these neighbors are not adjacent to the winner. If the maximum distance k between the winner and its neighboring neurons is 1, and the neuron 75 is the winner, then these neurons marked in green are the neighbors of this winner. Next, let's implement a SOM model to cluster the Iris dataset. Load and normalize the Iris dataset. Since the Iris data has 4 features, the input layer also has 4 neurons. Set the size of the competitive layer to 50 by 50. And randomly initialize the weights between the input layer and the competitive layer. Set the learning rate alpha to 0.05 and the maximum distance between the winner and its neighbors to 20. Like the competitive learning model in the previous video, we write a function to find the winner neuron based on distance as follows. And as we saw in the previous slide, we write the function to find the neighbors as follows. Then, we write a function that updates the weights connected to the winner neuron and its neighbors using the competitive learning rule as follows. Now we iteratively update the weights. Sample 100 data points from the Iris dataset. And find the winner neuron for each data point. Then we find the neighbors of that winner neuron. Next, we update the weights connected to the winner and its neighboring neurons. And we use the distance between this data point dx and the weights connected to the winner as the error of this model. The shorter this distance, the better the model's performance. It is widely used to evaluate the performance of unsupervised learning models and reduce the maximum distance between the winner and its neighbors by 1. To prevent this from decreasing too quickly, we decrease it by 1 every 3 iterations. Repeat this process 300 times. This is the learning process of SOAM. Next, we perform the prediction or mapping process. Find the 2D coordinates of the winner neurons for given data points in the competitive layer. These coordinates are the self-organizing map for the Iris dataset. And we visualize this map. The results are as follows. The error decreases gradually during training, as shown in this figure. The self-organizing map for the Iris dataset is as follows. The data points marked with blue circles belong to the Iris setosa group. The data points marked with orange squares belong to the versicolor group. And the data points marked with green triangles belong to the Virginica group. You can see that the 4-dimensional feature data points are clustered in this 2-dimensional space. Let's run this code. We got the following results. Finally, let's implement the SOAM model to cluster the MNIST digits. Load and normalize the MNIST dataset. This will take a long time, so we will only use 2000 NIST images. We set the size of the competitive layer to 100 by 100. The rest is the same as the previous code. This part is also very similar to the previous code, so I will skip the explanation. Let's check the results. The error decreases gradually during training, as shown in this figure. The self-organizing map for the MNIST dataset is as follows. The MNIST images of digit 0 are located in this area on this map. And the images of digit 1 are located here. You can see that the 780 4-dimensional feature data points are clustered in this 2-dimensional space. In this video, we looked at self-organizing maps. So far, we have looked at models related to Hebbian learning that do not use backpropagation through a total of 12 videos.